Hey everyone, welcome back, and today let's solve Leetcode problem 1072 titled Flip Columns for Maximum Number of Equal Rows, the daily Leetcode challenge problem. So we're given an m by n dimensions binary matrix, and we can choose any number of columns in the matrix and flip every cell in that column, which basically means changing the value of the cell from 0 to 1 or from 1 to 0. So we need to return the maximum number of rows that have all values equal after some number of flips. So in example 1, we have our input matrix to be the following. It's a 2 by 2 matrix, and we output 1. Why is that? Well, because after flipping exactly 0 values, because that's the most optimal way we can do this, we'll have exactly, at best, no matter how many ways we flip it, one row, again, at best case, that has all the values equal. It's this row right here. It has two ones, and regardless of how else we choose to flip it, we're not going to have both of these rows have equal values, basically all zeros or all ones. In example 2, we have our input matrix to be the same dimensions, but in this case, we'd output 2. Because if we flip the values in the first column here, then both rows would indeed have equal values, 1, 0. In example 3, we have our input matrix to be these following. It's 0, 0, 0, 0, 0, 1, and 1, 1, 0 for our rows. And in this case, we can output 2. Why is that? Because after flipping all the different values in the first two columns, then the last two rows would have equal values, right? They would both be 1, 1, 0, right? This 0 would become a 1, this 0 would also become a 1, and this 1 would become a 0, which is equal to 1, 1, 0. And this would be 1, 1, 1, but of course that doesn't match anything else, and so we'd output a best case or max scenario of 2 equal rows with equal values. So with that examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to solve this problem efficiently, we're actually going to be using a counter from in Python. It's called the collections module. That's not really important in Leetcode specifically because it already has all these pre-packages and modules directly imported in your code editor. But just for best practice, I just want to kind of let you guys know which module it's actually from, the counter data structure, right? And we're going to use this counter to actually track how many times each of our patterns in all the different rows actually appears or has a frequency across all the different rows. Okay, and essentially by storing both the original pattern and its flipped version, where we flip all these zeros to ones and vice versa in the rows, we can handle rows that are equivalent after some number of flips, right? After flipping a row, we can handle rows if they're equivalent or not from their flipped form to their original form. Okay, and finally, once we've computed all of that for all the flipped and non-flipped original rows and their computations, we can simply return the maximum count of any pattern, right? Which is because that's going to represent the maximum number of equivalent rows. So with that out of the way, let's go ahead and dive straight into the code here. So like I was talking about before, I'm going to import the collections module here to actually get our counter data structure. So in Python, it would be from the collections module, we want to import our counter feature, right? This is simply just grabbing the counter class from our collections module, right? And this is basically just a specialized dictionary which is going to enable us to count the occurrences of row patterns efficiently, right? To kind of generalize how counter works, let me actually comment this out. Counter simply basically stores the frequency of each distinct value in a data structure, primarily used in strings and lists, or arrays, if you will, right? And just to make sure I didn't spell anything wrong here, that looks to be right. Okay, now, once we've done that, now let's actually kind of go into the main part of this code. So I'm going to initialize our pattern count, like I talked about just now, to be initialized to an empty counter. Right, and yes, if you guys haven't actually initialized variables with empty counters, this is actually allowed, and this is kind of aligning with Python syntax. So what does this do? We're simply going to use this pattern count counter or dictionary, specialized dictionary, if you will, to actually store counts of all the different patterns and their flipped patterns as well. And note that their flipped patterns basically just signifies those rows when we actually flip every 0 to a 1 and every 1 to a 0 in that specific column. Okay, so once we do that, now let's actually iterate over each row. So for every row in our matrix input array, or 2D array, rather, simply iterating through each row of our input matrix, we want to instantiate our pattern to be a tuple for it to be hashable and inserted in our counter of the current row. And once we've initialized this pattern, we want to set our flipped pattern to basically be a tuple again, so we can actually have it in our dictionary, because we want tuples as our keys and key value pairs of 1 minus x for every x in the row, right? This is kind of, I think it's called list comprehension, in this case dictionary comprehension. I'm not sure if that's applicable here, but that's what I assume this is called. But what are we doing here? Well, first of all, on line 7, we're simply converting our current row that we're iterating through to make it a tuple. Why? Again, so it's hashable, so it can be used as a key in our counter. Once we've actually instantiated that key, our pattern for this current row's regular or original form without flipping it as a tuple, then we want to generate a flip pattern, or a flipped version of this current row, where each 0 becomes a 1 and each 1 becomes a 0. And this is kind of a quick way to do that. We simply loop through all the different elements in this row and convert it to 1 minus x. Okay, and we're simply making that a tuple. Okay, we're making that a tuple. Now, the reason why 1 minus x works is because, assume we had x to be 0 in this iteration, 1 minus 0 is simply 1. And so this 0 would then become 1 minus 0, or a 1. And if x is equal to 1, well, 1 minus 1 when x is 1 is 0. So this 1 would become 1 minus 1, or simply just 0, right? That's kind of a quick, kind of nice way to convert zeros to ones and ones to 0 using this tuple hashable key value pair for every single x in this current row of 1 minus x, and making it a tuple again, so it's hashable. Rather, this flipped pattern is hashable to be inserted as a key value pair in our dictionary, okay, in our pattern count dictionary. So once we've actually initialized this flipped pattern generation and the pattern itself for the current row, we want to actually increment its frequency in our counter. So we can update our counter by simply saying pattern count. Again, note that this is our hash map at that pattern, right, at the pattern index, to be incremented by 1. We're simply incrementing its frequency by 1. And we're going to do the same thing for the flipped pattern here, right? The pattern, or the generation of the pattern that we just flipped for the current row in this iteration of our matrix. So we want to set pattern count at the flipped pattern. Again, just simply a flip pattern of all the different 1s to 0s and 0s to 1s in our current row for this hash map to be incremented by 1. We want to simply increment its frequency by 1. So to reiterate, we're simply, again, incrementing the count of the pattern, or the frequency of the pattern, the original row in our pattern count hash map for the current row. And similarly, we have to increment the count of our flipped pattern, right? We're ensuring that both our original row and our flip rows contribute equally, or have an equal contribution of their frequencies in our hash map pattern count. So once we've done that, we simply have to return the maximum count of any row that we actually flipped or didn't flip. So we need to return the maximum value of the pattern count's values. And in Python, it's pretty straightforward to do that. We simply have to return the maximum of pattern count dot values using our dot operator for hash maps and in Python in regular. Why? Because again, just if you guys haven't used Python before, pattern count dot values is simply going to give us a list of all the different counts or key value pairs actually stored in our counter, right? Pattern count counter. And why does max actually work? Because that's going to tell us or find the largest count, and the largest count is going to represent the maximum number of equivalent rows, either in flipped form after flipping it, or in its original form without flipping it, right? As we saw in input example 1, we didn't have to flip any values to get our maximum count, but in examples 2 and 3, we did have to flip values, okay? That's kind of how that quickly works. So kind of just a quick reiteration of how this solution actually works. So a quick high-level rundown of why this works. Simply, for every single row in our matrix, we simply have to calculate two of its versions. Either the first case or the first choice where we just don't flip any values, we have its original row, the original pattern, or we can flip all the zeros to ones and ones to zero on using this kind of clever dictionary comprehension, you can say, right, where we simply have the flipped pattern, right? We have the flipped pattern of the row if we want to flip all the elements to be kind of opposites of themselves, zeros to ones and ones to zero, and we also have our initial choice of just a pattern. And once we've gotten these two patterns, we have to actually add them to their counter or increment their frequency to the counter. And what is that? It's simply going to aggregate, I don't know how to say that word, how often each pattern, or the flipped and the regular pattern, actually appears across our matrix, right? And all the rows that are flip equivalent are going to contribute to that same pattern's count, right? And we can basically guaranteed return the maximum of the pattern count values, because that's going to give us the maximum number of flip equivalent forms, right? That's going to give us which form, either flipped or non-flipped, of any row can actually be achieved the most, right, after flipping or not flipping any row to achieve that specific pattern. And so we can just return the maximum value in our counter, because that's going to give us the maximum occurrence of of one row either being flipped or non-flipped based on the rows that we iterate through. So as you can see, if I were to submit this, unless I made any syntax errors here, this should be accepted. Okay, let's see what I did wrong here. There should be an N here. I don't know why I forget my N's half the time, but now this should work. And as you can see, this is just about as efficient as you can get. So for the time complexity of this solution, this is going to be a big O of m times n solution. M is going to be the number of rows, and n is going to be number of columns, right? Because we have to actually process each row, and that's going to involve generating our flip pattern, which is a big O of n or linear time solution, and updating our counter, which is a constant time solution. And for our space complexity, the counter is going to store up to m unique patterns in the worst case possible, and each pattern is going to have a size of n, our m by n input matrix. And so the total space complexity is also going to be a big O of m times n solution for that pattern count dictionary. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.